Donc, bonjour à tous et à toutes et bienvenue au Club Math de l'Université de Montréal. Cette semaine, on a le grand honneur d'accueillir le professeur James Maynard de l'Université d'Oxford, une véritable sommité mondiale en théorie des nombres analytiques. Cet ancien post-doctorant de l'UDM donnera un exposé sur un sujet qu'il affectionne particulièrement, les patterns dans les nombres premiers. Nous vous invitons à avoir vos caméras ouvertes pendant la conférence et vous pouvez vous poser des questions quand vous voulez. Maintenant en anglais, parce que la conférence sera en anglais. Hello everyone and welcome to the Club Math of the University of Montreal. This week, we have the great honor of welcoming Professor James Maynard of the University of Oxford, a true world leader in analytical number theory. This former postdoctoral fellow of UDM will give us a presentation on a subject he especially likes, the pattern in prime numbers. We invite you to have your cameras open during the conference and you can ask questions whenever you want. Thank you so much, Professor Maynard, for accepting our invitation. The floor is yours.
Okay, thank you very much for the two introductions, and thanks a lot for all of you guys for coming along to listen for me to speak. This is supposed to be a fairly laid back talk, so yeah, I'd just like to reiterate that it's totally fine for you to interrupt me and ask questions and things at any time. I would much prefer a bit of interaction than waiting just for all the questions at the end or something like that. And I would like to talk about patterns in prime numbers. So this was something that I very much liked and was one of the main things that I was working on when I was in Montreal back about 7 or 8 years ago now. And maybe the key motivation for the sorts of things that I like to think about can be seen in an address of the International Congress of Mathematics by Landau a bit over 100 years ago. So Landau was speaking to all the leading mathematicians and he posed 4 problems that were unattackable by the present state of mathematics at the time back in 1912. So the first question is Goldbach's conjecture, which asks, can every even integer, which is bigger than 2, be written as the sum of 2 prime numbers? Then his second question was the so-called twin prime conjecture. Are there infinitely many primes p such that p plus 2 is also a prime number? So pairs of primes that differ by exactly 2. His third question is known as Legendre's conjecture, which asked, is there always a prime between any 2 consecutive squares? And then his third question was, are there infinitely many prime values of the polynomial x squared plus 1? So are there infinitely many primes which are 1 more than a square number? So all of these are very simple to state problems about prime numbers, and at least 100 years ago in 1912, these questions were quite well known but seemed completely outside of the available technology. And the slightly unfortunate thing is that now, in 2021, so over 100 years later, all 4 of these questions still are open and all still seem to be well beyond our current methods. So I feel that these are 4 pretty simple looking natural problems, but it turns out that these are all very complicated 100-year-old problems that some of the best mathematicians in history have thought about, but been unable to make real major progress on. So questions like these are both big motivations for me because, there are these famous problems that we just haven't been able to solve, but it's also a little bit embarrassing for someone like me who likes to think about these questions, that a natural question that maybe a high school kid could ask you about prime numbers, we just don't know how to answer at all. So some of the things that I'd like to talk about in this talk is maybe these questions seem slightly artificial. So why should we even care about these questions in the first place? Then why are we so rubbish at proving anything about them? That if they're such simple to state problems, you might well hope that there should be some fairly simple argument. And so why is it that this seems to have evaded the best minds of mathematicians? And it turns out that for all of these questions, we're very confident that the answer is yes, there are prime numbers with these special properties. But how can we be so confident that we know what the right answer is if we can't prove them? Are we just deluding ourselves? If we're so rubbish at proving the results, how can we be confident that we can at least guess what the right answer is? So those are maybe the three main things that I'd like to talk about today, and also link them to some slightly more current research that at least makes some partial progress on some of these questions. So let's start off with thinking about why should we care about these questions? Well, it's always a bit sort of difficult as a meta thing to justify why one maths problem is more important or less important than another maths problem. But here are at least four justifications that I have for these questions. So maybe the most basic motivation for studying them is that I find these simple to state questions about prime numbers just inherently intellectually appealing. If you want to understand prime numbers, then say understanding the size of the gaps between prime numbers is the most basic question that is one of the most basic questions that I can think of. And you can't claim that you understand prime numbers if you don't understand questions that are somewhat like these. So I find them inherently appealing, but I guess as a meta result, it's historically been the case that often mathematics has been motivated by some somewhat artificial looking questions. So Fermat's last theorem is maybe a good example of this, that it's led to some absolutely beautiful and fundamental deep mathematics, because Fermat's last theorem was this heavily studied problem, but on the face of it, maybe Fermat's last theorem looks somewhat obscure and artificial, but these obscure artificial questions often lead to absolutely beautiful and foundational general theory. And I feel that the same is true for Landau's questions, that if in the future we're able to prove Landau's questions, even if Landau's questions were originally somewhat artificial, whoever proves them will have developed a great insights and come up with a powerful, more general theory that really understands something about the prime numbers. And maybe that's more important than solving the Landau problem. Maybe on a more direct justification, all of Landau's problems mix some part of multiplication with some part of addition. That prime numbers are naturally multiplicative objects. They're defined through multiplication. But one of the reasons that Landau's problems are difficult is that it's mixing prime numbers, which are multiplicative objects, and addition. So we're looking at whether p plus 2 is a prime number or not. And it's that plus 2 which makes it a difficult question. If it was just a purely multiplicative question, it would be asking something like, is 2 times p ever a prime number? And that would be a very trivial question to answer. And there's lots of different examples in mathematics of where when you mix multiplication and addition, you can have surprisingly complicated but beautiful general theories coming out of this. But maybe the strongest motivation I have is that, to me, prime numbers are some of the most fundamental and interesting objects in mathematics. These are just totally basic questions about the distribution of prime numbers. And so I claim that prime numbers are inherently interesting and important in pure mathematics, They relate to all kinds of other questions, both in other areas of mathematics, but also in computer science and engineering and physics. And if you want to understand the prime numbers, then you want to understand the distribution of the primes. And so you want to understand basic questions like these. And all of Landau's questions can be phrased as trying to solve some sort of linear or polynomial equation where some of your variables are prime numbers. So for example, the twin prime conjecture is looking at the equation x minus y equals 2, and you're trying to find solutions x and y where both x and y are restricted to being prime numbers. Similarly, Goldbach's conjecture is asking if for every value of capital N, you can solve plus y equals 2 times capital N, where x and y are prime numbers. And this means that both the Goldbach conjecture and the twin prime conjecture actually look very similar from the point of view of lots of different techniques, because it is a linear equation in two variables x and y, where x and y are both restricted to being prime numbers. And so studying these questions, maybe from this slightly different viewpoint, means that you can see links between them. And it's certainly currently believed that if you could solve Goldbach's conjecture, it's quite likely that whatever proof you have of Goldbach's conjecture might well work for twin prime conjecture as well. And so it might well be the case that it's a buy one, get one free for Landau's problems. If you can solve one of them, you can solve another one. Similarly, there's links between primes between consecutive squares and primes of the form n squared plus 1. So I think there's a, so primes between consecutive squares is trying to solve the equation x equals n squared plus y for some given value of n, where x has to be a prime number and y has to be fairly small. It has to be at most 2 times n. And this is somewhat similar to prime values of the form n squared plus 1. So that's solving x equals y squared plus 1, where x is a prime number. And so again, it might be a case that you see links between these equations by viewing them as polynomial equations. And this might mean that whatever method you have for one works for some of the others as well. So the key reason that I view primes as inherently interesting objects, which is the key reason that I view Landau's problems as inherently interesting problems, is that prime numbers are the atoms of integers from the point of view of multiplication. So all whole numbers are made up of prime numbers mixed together. So this often has the fancy title, the fundamental theorem of arithmetic, that every integer which is bigger than 1 can be written as a product of prime numbers. And moreover, this product is unique up to the rearranging the order of the primes in the product. So at first sight, this looks like some fairly odd artificial statement that maybe shouldn't have such grand a title as the fundamental theorem of arithmetic. But the key point is that this means that all whole numbers are built out of prime numbers. And so the dream is you might be able to have a general machine where if you have some difficult problem about whole numbers, you can reduce it just to a simpler question about prime numbers. And you might use your understanding of prime numbers to solve that question about prime numbers and therefore solve the original problem about whole numbers. So mathematicians are inherently lazy people. Rather than going through lots and lots of cases or working really hard to solve a difficult problem, the great dream would be that we can come up with some very clever argument that turns a difficult problem into a much easier problem. And for lots of questions about whole numbers, it turns out that it can often be much easier to relate it to a problem about prime numbers and then to try and solve a problem about prime numbers. So let me take an example of this. And my example is going to be Fermat's last theorem. So Fermat's last theorem, as I'm sure most of you know, is the claim that there are no integer solutions to the equation x to the n plus y to the n is equal to z to the n, with when n is some number which is some integer bigger than 2, apart from the obvious ones when one of them is equal to 0. So obviously you could set x to be equal to 0, and then y to be equal to z, and then you have a solution. But apart from the ones when one of the variables is equal to 0, there should be no integer solutions whatsoever. So this is a question that is just to do with whole numbers, and it's one of the most famous problems in the whole of mathematics. But it's a very simple reduction that if you want to solve Fermat's last theorem, it's sufficient to just solve Fermat's last theorem when n is a prime number. So the reduction of this only uses high school algebra, so I'll just give it here. So imagine that Fermat's last theorem is false, and it's false for some composite number. So imagine n is a times b, and there's some solution x to the n plus y to the n equals z to the n. Well, since x to the power b to the power a is x to the power b times a, which is x to the power n, I can rewrite x to the n plus y to the n equals z to the n as x to the b to the power a plus y to the power b to the power a equals z to the power b to the power a. So therefore, if x, y, and z are some solution to Fermat's last theorem with exponent n, x to the power b, y to the power b, z to the power b is a solution when the exponent is a. And this means that if you had a counterexample to Fermat's last theorem with exponent n, then you automatically get a counterexample to Fermat's last theorem for every prime factor of n.
Excuse me, this doesn't seem to work when n equals 4, because being able to find an example when one of the factors would be 2, this is not surprising. So for n equals 4, I don't think this argument holds.
Yeah, so you've preempted me, which is my bullet point 4. But so far, what I've shown, I think is totally correct, that if I have a solution to x to the n plus y to the n is equal to z to the n, then I also get a solution when n is replaced by any prime factor of n. So if I knew that Fermat's last theorem was true whenever n is a prime number, then I would be done. Apart from, I have to be a little bit careful about the exponent 2, because we know from Pythagoras' theorem there are indeed solutions to x squared plus y squared equals z squared. And so if I knew Fermat's last theorem whenever n is a prime number, I would be done. Apart from powers of 2, I would have to be careful about Fermat's last theorem for powers of 2. But it turns out that the case of n equals 4 is an old result of Fermat, that he already knew how to do n equals 4 using an ingenious argument, which is now known as descent. So already Fermat knew how to do n equals 4, and with Fermat's result on n equals 4, it's sufficient to just prove Fermat's last theorem whenever n is a prime number. Now, at first sight, it doesn't seem clear that Fermat's last theorem for a general integer n is any easier or harder than Fermat's last theorem just when n is a prime number. But it turns out that this reduction to just considering prime numbers is absolutely crucial, and this is the first step in Andrew Wiles's argument. So unfortunately, there's not quite enough space on this slide to give the complete proof of Fermat's last theorem. But this is essentially the first step in Andrew Wiles's proof. And the key point here is that we started out with a problem to do with whole numbers, and we reduced it to a problem to do with prime numbers, and the problem to do with prime numbers is somehow simpler in various technical senses. So Wiles's work was an absolute pinnacle of very modern mathematical techniques, but once you've reduced it to a question about prime numbers, there's various questions about prime numbers that can allow you to make partial progress. So just sticking with Fermat's last theorem for a moment, there was some important work done by Sophie Germain back in the 1820s, so 200 years ago, way before Wiles's work. And she was looking at Fermat's last theorem, and from the slide before, we only need to consider the case when n is a prime number. So if n is a prime number p, with the additional property that 2p plus 1 is a prime number, then Sophie Germain showed that there's no solutions to Fermat's last theorem apart from the ones where xyz, or here abc, is 0 mod p, so it's a multiple of p. This is known as the first case of Fermat's last theorem. People imagined that you only need to consider Fermat's last theorem when n is a prime number, and they imagined that you would first solve the first case of Fermat's last theorem, which is solutions when ABC is not a multiple of P, and then that should lead to the second case of Fermat's last theorem when ABC is possibly a multiple of P. So people thought that this was the important first case to try and solve, and Sophie Germain came up with the first sort of general technique for attacking this problem for arbitrary exponents n, and she showed that we only need to consider n being a prime number, and when 2n plus 1 is also a prime number, then you can solve this first case of Fermat's last theorem. And based on this, she was able to show that for many different exponents, Fermat's last theorem was indeed true. So she was able to go beyond what her peers were able to do. But one natural question, as soon as you see Sophie Germain's result, is how many primes p are there such that 2p plus 1 is a prime? If it was the case that for every prime number, 2p plus 1 is a prime number, then Sophie Germain's theorem would almost solve Fermat's last theorem already in the 1820s. If, on the other hand, there was only a finite number of primes p such that 2p plus 1 is a prime number, then Sophie Germain's theorem wouldn't actually have so much content, and it would only work in a finite number of cases. So already with Sophie Germain's work, starting off with this problem about Fermat's last theorem, which was then the most famous problem in the whole of mathematics, it quickly led you to questions about patterns in the primes. How many primes p are there such that 2p plus 1 is a prime? And we can see that this is actually, again, a linear equation in two prime variables, that this is looking to solve 2x plus 1 equals y with x and y prime variables. And so in many ways, it's very similar to the twin prime conjecture or Goldbach's conjecture. And indeed, we still don't know how to answer this question about how many primes are there such that 2p plus 1 is prime, but we would believe that there should be infinitely many such primes. I'd now like to skip to a completely different example of the role of prime numbers and patterns in the primes. And that's to do with internet security. So imagine you want to buy something from Amazon on your computer. Well, when you put in your credit card details, you want your credit card details to be secure, so some hacker isn't able to get your credit card details and then use your credit card details to buy all kinds of things for themselves. So to make sure whatever you buy on Amazon is secure, your computer encrypts the number, so it's very difficult for a hacker to work out what your credit card details indeed are. And it turns out that the manipulations encode your credit card number as a number, and because the cryptographic protocols typically multiply lots of numbers together, it involves whole numbers and multiplication. And so you might hope that the whole situation can be reduced to some questions about prime numbers if you're interested in how can you make a secure cryptographic system and whether a given cryptographic system is secure or not. So in particular, this is true of one of the most common cryptographic systems, and you can analyze this, and because it involves multiplying whole numbers together, the situation can be understood pretty well via looking at prime numbers. And the whole cryptographic security boils down to a simple question about factoring a number. And it turns out that for this particular system, if you're a hacker, you can hack the credit card details efficiently. If given some large number, you can write it as a product of prime numbers. So we saw from the fundamental theorem of arithmetic that every whole number can be written as a product of prime numbers. If you can do this quickly, then you can hack one of the most important cryptographic schemes. So for example, if I gave you the number 449,623, the question is, what are its prime factors? So maybe one of you in the audience is pretty quick with mental arithmetic, and maybe you can guess pretty quickly that 449,623 can be written as 521 times 863. And if you or your computer can do this very quickly, then using this cryptographic system, if I'd chosen the number 449,623, you'd be able to hack all my credit card details. However, we believe that this process of turning a number into its prime factors is very difficult when the numbers are very large. So as a concrete example, there are these various challenge problems. So here's some large number with a large number of digits, but it's just some explicit number that I can write down, and it does fit on one slide. And if you can write this number as a product of prime factors, then you win $75,000. But no one's been able to do this so far. So if any of you can see the two prime factors of this number, and you can write it as just a product of two numbers, you can claim $75,000. So maybe if you're bored during my talk, you can think about this in your spare time. But the point here is that even with huge computational resources, no computer knows how to factor this into two prime numbers. And this is a big number, but it's not so big. You can multiply this with some other number of the same size, and your computer can give you the answer instantly. So your computer can add and multiply numbers of this size fine, but it can't factor it. And we believe that this is because factoring is a difficult problem for computers. However, it's a fact due to Pollard that if the original number that you had has a prime factor p such that p minus 1 itself only has very small prime factors, then there's a trick which means that you can factor this number very easily. So for example, I can consider the number 2 times 3 times 4 times 5 up to times 320 plus 1. It turns out that this is a prime number. You can check that on a computer. And by construction here, p minus 1 is just 2 times 3 times 4 times 5 up to times 320. And so it only has small prime factors. Certainly all the prime factors have to be smaller than 320. And you can choose some large number q, which is multiplied by p. And even if I didn't know p, I can use this factor Pollard to work out the full prime factorization of n very easily. And the point here is that this number p is way, way, way bigger than the number I put on the previous slide. So this is an example where you could choose some absolutely huge number, but your computer could use this Pollard algorithm and it would recover the prime factorization because you chose a bad number to start with. You chose a number that had a prime factor p, where p minus 1 only had small prime factors. And so if I chose any number of this form, you could just run your computer, not knowing that my number is a multiple of p, and you could recover that p is a prime factor and what the other factor q is basically instantly. So if I'm concerned by this, I would want to make sure that I'm going to choose a number n where the prime factors are such that p minus 1 doesn't have lots of small prime factors, because otherwise my credit card details are very easy to hack. And so we expect that it should be very rare that you accidentally choose a large number where you're in this bad situation, but some people. And so some cryptographic algorithms deliberately only choose integers n where their prime factors are so-called safe primes, which are primes p such that p minus 1 divided by 2 is a prime number. So p minus 1 is going to be a multiple of 2. And so the furthest you could possibly be away from p minus 1 having lots of small prime factors is if p minus 1 divided by 2 itself is a prime number. So this actually happens in real cryptographic algorithms. So OpenSSL is one of the most common internet security toolkits, and one of the operations that your computer can use with OpenSSL is to choose safe primes, and this generates a prime p such that p minus 1 divided by 2 is also a prime number. But this would be an absolutely terrible cryptographic thing to use if there were hardly any safe primes. If there were only 5 safe primes in the world, then I know I'm only going to generate some list of 5 numbers, and some hacker could just have this list of 5 numbers, and he would always know that this is going to be one of the prime factors. And so it would make the cryptographic scheme very insecure. So a natural question, if you're considering using so-called safe primes, is whether safe primes are in fact safe. And one certain question as to whether safe primes are safe would be, how many safe primes are there? And another way of saying that is, how many primes p are there such that p minus 1 divided by 2 is a prime number? So the interesting thing here is that maybe you'll recognize that this question to do with internet security and safe primes is in fact exactly the same question that we ran into when we were looking at Fermat's last theorem and Sophie Germain's work on Fermat's last theorem. In both cases, we were reduced to asking, are there solutions to 2x plus 1 equals y in prime numbers? And this question is just that same question rephrased. So we've seen 2 very different cases, one example in pure maths and one example in internet security, which involved just whole numbers being multiplied together. But in both cases, we were able to reduce the whole problem into some question about prime numbers. And we could say something non-trivial about this question, depending on the distribution of patterns of primes. But in both cases, we were led to what turned out to be exactly the same question about solutions to 2x plus 1 equals y in prime numbers. So we analyzed these 2 different situations, and in both questions, it led us to a question about the distribution of patterns of primes that is an open problem and it's been open for 100 years and we don't know how to solve it. So these are 2 different examples of questions to do with whole numbers being directly related to questions to do with the patterns of prime numbers. So maybe this is an example of how prime numbers are really quite fundamental objects that appear in all kinds of different places, both in pure mathematics, but also in real world cryptographic algorithms. And how questions about patterns of primes really appear in the real world as well. Okay, so what about some of my other questions that I put up at the beginning? Why are these questions about primes hard? And why are we confident that we know the answer to these questions if we can't prove anything about them? Well, one of the reasons that I said the questions were somehow interesting on some meta level was that primes are multiplicative objects, but Landau's problems ask about additive questions. And so it's mixing multiplication and addition. And that reason why they're interesting also makes these questions hard, that it's very natural to study primes from a multiplicative viewpoint, but it's very difficult to study additive properties of the primes. And it's this mixture of multiplication and addition that means we don't have very natural techniques for looking and studying Landau's problems. The other key reason that we think these problems are hard is that we don't think there's some deep conceptual structural reason as to why these questions are true. We essentially think they're true for no good reason whatsoever. So if something's true for a good reason, then it's often much easier to prove it to be true, because you just need to work out what that good reason is, and that good reason should automatically lead to a proof. But if there's no good reason for something to be true, it's much harder, that somehow we believe that if these questions weren't true, there would have to be some bizarre conspiracy in the distribution of prime numbers. But that means to prove these Landau questions, what you really have to prove is that there isn't one of these bizarre conspiracies in the prime numbers. But ruling out lots of different possible conspiracy theories is really a much harder mathematical challenge than discovering what a good answer, what the real reason behind something is, and just giving that real reason. And so just as in the real world, it's difficult to constantly shoot down different conspiracy theories, that it's much easier to come up with a conspiracy theory than it is to conclusively rule it out. In mathematics, it's also difficult to rule out these conspiracies. And it's because we're trying to rule out conspiracies rather than to come up with a good reason why these answers are true, that it makes them very difficult to prove. But the reason that despite this, we are very confident, and why we think that there would have to be a very strange conspiracy if they weren't true, is because in a statistical sense, the primes seem to behave as if they were just randomly picked numbers without many important properties at all. And this means that you can come up with guesses about what the answers to various questions about primes should be based on random models. And these random models then make kind of concrete predictions of not just whether there should be infinitely many twin primes, but precisely how many twin primes we think there should be. And because these models make very accurate and precise numerical predictions, you can simply test them on a computer. And so you can take a much more experimental view of the whole question. And it turns out that these random models make exceptionally good numerical predictions. So if you want to predict the number of primes less than 1 billion, or the number of twin primes less than 1 billion, these numerical random models can make some guess based on the assumption that the primes statistically look as if they were random numbers, and you can then actually count the number of primes or twin primes up to 1 billion, and these two things match up as well as you could possibly hope. And so it's because these random models make such good predictions that we really think that that these are capturing all the important structural properties of the primes, and there would have to be some very bizarre conspiracy for the primes to not behave somewhat similarly to the random model in a statistical sense. That any sequence that has a few properties in common with the primes would typically look like a random model, and so the primes have to look very bizarre and have some very special features that we don't understand if they didn't follow these random models. And all numerical evidence seems to indicate they do. Of course, this also means that in some sense, it would be much, much more interesting if one of those Landau problems was false and there were only finitely many twin primes, because this would mean that there is some deep structural conspiracy in the primes that means statistically they behave very differently to the random models. And this would mean that there's some very important fundamental property of prime numbers, which is totally different to what we currently believe about primes. So it would completely change our beliefs about how the primes are distributed and how to think about prime numbers. So if anything, it would be more fun if one of those questions was false. But let's see an example of these sort of predictions in practice. So a very natural way of thinking about primes is to ask how many primes are there? And you've probably seen often Euclid's proof that there are infinitely many prime numbers. But that on its own doesn't really make any quantitative prediction about how many prime numbers there are of any given size. And so it's difficult to sort of numerically test whether whether numbers less than a billion are consistent with Euclid's theorem that there are infinitely many primes or not. That you see that there seems to be lots of primes less than a billion, but the density of the primes is dropping off. So it's maybe difficult to conclude something very precise. However, Gauss, remarkably, just when he was a teenager, I think he was 16 when he made this prediction, he said that if you take some large number x, then around x, the primes should occur with density about 1 over log x. So he made this prediction just from looking at long lists of numerical tables about prime numbers. And this, if you take Gauss's prediction, this makes a quantitative prediction that you can then test numerically. So if the primes around t occurred with density 1 over log t, then you'd expect the number of primes up to some large number x to look roughly like the integral of 1 over t between maybe 2, which is the smallest prime, and x. And this then gives a precise quantitative guess, which, as a highlight of modern mathematics, we know that the number of primes up to x is roughly given by Gauss's guess. But if you look at the numerics, they actually fit much better than any of the theorems we're able to prove. So if you want to calculate the number of primes which are less than 10 to the 10, you can just test this on a computer, and your computer will tell you there's 455,052,511 primes less than 10 to the 10. If you just look at Gauss's guess function, which is just the integral of 1 over log t between 2 and 10 to the 10, so this is some smooth, simple function, this would guess that the number of primes should be about 455,055,613.8, blah, 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 blah. And so it's not given exactly the right answer. The difference is about 3,000, but it's off by less than 0.0007%. And so it's really a remarkably good guess, because this is such a simple function, whereas we think the count of the primes less than x is some horrible complicated function, but we can approximate it to a remarkable level of accuracy by this simple guess of Gauss. And it turns out that this guess of Gauss and the fact that these are very accurate is very closely related to maybe the most famous and important open problem in mathematics, the Riemann hypothesis. So for slightly technical reasons, often it's easier to counteract the fact that these primes have decreasing density of 1 over log x around x to count all primes with a weight log p. So count a prime p with a weight log p instead of 1, just for technical reasons. This doesn't matter too much, but it makes a few things nicer. And if you do this, then basically my favorite formula in the whole of mathematics is so-called Riemann's explicit formula. If you want to count the primes up to x, and okay, again, it's slightly annoying that you have to count prime squares and prime cubes and things, but essentially if you count the primes up to x with weight log p, then there is a totally explicit formula for this in terms of the so-called zeros of the Riemann zeta function. So it doesn't really matter what they are, but there are some special complex numbers, and if you want to understand the number of primes up to x, you can understand this very complicated object in prime number theory perfectly if you just find the zeros of some certain analytic function. And so in particular, the zeros of this function tell us exactly where the prime numbers are, that there's no error terms or anything here. And if Gauss's guess is correct, it's saying that the number of primes up to x should be roughly given by x. And so all of these terms from the zeros of the Riemann zeta function should be thought of as small correction terms, and that's measuring the error in Gauss's guess. So it's maybe easiest to see this as a picture because we can think of the right-hand side as a sum of different waves where we have one wave for every zero of the Riemann zeta function. And so this is what Marcus de Sautoy calls the music of the primes. So here in blue, I've drawn the count of primes up to x, where we're counting primes with weight log p. So this is just a step function, and it jumps up whenever we get to a prime number. And the x-axis scale here is just going between 0 and 20, basically. Maybe it's 7 and 20. And in red, I put Gauss's guess. So Gauss's guess, when we're counting with this weight log p, is just a straight line. And you can see that the straight line matches this step function fairly accurately. But we know that the true formula from Riemann's explicit formula, there's these correction terms from waves coming from the Riemann zeta function. And so we can start adding in some of these waves. So I could take in the first 10 zeros, which gives us a better approximation. You can see particularly for small numbers here that this is following this step function much more closely. It's obviously not a perfect fit because the red line, which is Gauss's guess plus the first 10 correction terms, is going to be some smooth continuous function, whereas the count of the primes is still this messy step function that has a jump whenever you get to a prime number. But we can then include the first 100 zeros, and we get a much better fit to this step function. And once we've included the first 1,000 zeros, we get an almost perfect fit. And we can see how these complex numbers, the zeros of the Riemann zeta function, are really telling us precisely where the primes are. And so each of these correction terms in my formula before was essentially x to the rho divided by rho, where rho is one of these complex numbers, which is a zero of the Riemann zeta function. And the size of x to the rho is just x to the real part of rho. So basically, all of these correction terms are very small, and Gauss's guess is a very, very good guess if all the zeros have small real parts. And this leads us to the Riemann hypothesis that says basically that all the so-called non-trivial zeros have as small a real part as you can possibly hope for, which turns out to be 1/2. And this is explaining why we had such a good guess between the count of primes up to x and Gauss's guess of this integral of 1 over log t. That if you assume the Riemann hypothesis, then this automatically gives that these two numbers which are of size x have to differ by something which is only of size about square root of x. So that's like saying they have to have the first half of their digits have to be correct. And it's only in the lower half of the digits that you really have any possible errors in this Gauss guess. And so the Riemann hypothesis essentially perfectly describes why Gauss's guess was so good. And moreover, it gives this very strong understanding of the large scale distribution of the prime numbers. And so this is why the Riemann hypothesis is viewed as one of the most important problems in mathematics. But I'd also like to think a little bit about the small scale structure of the prime numbers. Okay, maybe I'll skip that slide in the interest of time. And in particular, the Riemann hypothesis says a lot if you're counting primes over large intervals. But what about if you look very closely and zoom in on the number line and look at just the gaps between prime numbers? So again, we have the prime number theorem, which is confirming that Gauss's guess is correct, which says the number of primes less than or equal to x is roughly Gauss's guess, which is roughly x divided by the logarithm of x. And it follows from the prime number theorem that if you look at primes of size x, then the average gap is of size about the logarithm of x. So we know that log of x gets bigger as x gets bigger. And so this means gradually the prime numbers on average get further and further apart from one another. And the proof of that is very straightforward from the prime number theorem, but maybe I'll skip it now. But even if on average the primes get further apart from one another, it might be that occasionally you get prime gaps which are rather smaller than the average, and maybe occasionally you get prime gaps that are rather bigger than the average. So a natural question is, are prime gaps always of size about log x when you're looking at primes of size x? Or can you have much smaller gaps? And can we classify maybe all prime gaps? So maybe the first thing to do is to start off trying to classify prime gaps of size 1, and that's quite straightforward. The only pair of primes which differ by exactly 1 is 2 and 3, and that's just because any two integers that differ by 1, one of them has to be odd and one of them has to be even, but 2 is the only even prime number. So the next thing to do would be to classify prime gaps of size 2, but we find numerically that there seem to be lots and lots of prime gaps of size 2. So the first pair bigger than 1,000 is 1,031, 1,033. First pair bigger than 1,000,000 is 1,037, 1,039. First pair bigger than 1 billion is 1,000,000,007, 1,000,000,009, and they just seem to keep on coming. And we see that this is just a restatement of the twin prime conjecture, that in fact, there isn't some finite list of prime gaps that differ by 2, there should be infinitely many of them. So maybe in the interest of time, I will skip a little bit about this, but again, we can consider Gauss's guess, which is saying that the primes occur with density about 1 over log x, and we can then try and guess what's the probability that both n and n plus 2 should be prime. And maybe a naive first guess would be that the probability of n being prime and n plus 2 being prime should look as if they're sort of maybe statistically independent on average. So the density should be about the product of the two probabilities. And so the probability that they're both prime should be modeled by 1 over log x squared. And that would give you some guess for the counter of twin primes that you can then numerically test in the same way that we could numerically test Gauss's guess. But it turns out that this guess is pretty rubbish. It's roughly of the right order of magnitude, but it gets the wrong results. And the reason it gets the wrong results is that it's not taken into account that all prime numbers are odd and no prime numbers are a multiple of 3 and so on. But this means you can refine your guess by taking into account that all prime numbers are odd. And if you do the same calculation, you get a slightly different guess, which is also numerically not very good. but taking into account that if n and n plus 2 are prime, primes must not only be odd, but not a multiple of 3, and not a multiple of 5, and not a multiple of 7, you can come up with some other different numerical guess, which is related to Gauss's guess, that the prime should come with, twin prime should come with some density, some constant divided by log t squared, where this constant depends on takes into account the fact that primes are odd and so on. And it turns out that, again, this gives really remarkably good numerical predictions. And so you can test this to huge height, as people have done, and this consistently is very accurate at estimating the number of twin primes. So you can do exactly the same thing, not just for primes that differ by 2, but for primes that differ by 4 or 6 or 8. And in fact, exactly the same pattern happens, that it's a conjecture of de Polignac generalizing the twin prime conjecture, that for any positive integer h, there should be infinitely many pairs of primes which differ by 2 times h. So h equals 1 is the twin prime conjecture, but this is a generalization. And again, for each positive integer h, you can make a precise numerical prediction for how many primes, such primes there should be. And this fits as well as you could possibly hope to imagine with numerical data. I think just to finish up, I want to mention some of the work that I did when I was in Montreal. So we can't prove de Polignac's conjecture, and we can't prove the twin prime conjecture, but we can prove some weak versions of the conjecture. So in particular, I and some collaborators showed that de Polignac's conjecture is true for at least some integer h between 1 and 123. So in particular, this means that there are infinitely many pairs of primes that differ by no more than 246. And so we do get these infinitely many small prime gaps that are much smaller than the average gap. Obviously, we believe that it should be true for any value of h between 1 and 123. And we believe that the twin prime conjecture should be true. We don't know how to prove that, but we are able to prove some weak versions of this twin prime conjecture. And if you're very optimistic and assume a certain technical conjecture in number theory, then you can improve this to prime gaps of size 6. And in fact, the method also using this technical conjecture relates the twin prime conjecture in some way to the Goldbach conjecture, that we can show that if you assume this technical conjecture, then either the twin prime conjecture is true, or Goldbach's conjecture is almost true, in the sense that for every large even integer n, which is either n plus 2 or n minus 2 is the sum of 2 primes. And so Goldbach's, either the twin prime conjecture is true, or Goldbach's conjecture is almost true. Of course, we expect both of these consequences to be true, but we know that they can't both be false on this technical conjecture. But I think I'm basically out of time now, but I've hopefully shown how these questions arise, but even some of these famous open problems, we can nonetheless still make some progress on. Thanks a lot for listening, and I'll pass over to questions.
As for the Riemann hypothesis, it's hard to factorize prime, and this expression with the Riemann hypothesis gives us an exact way to calculate the prime counting function. Is there a computational advantage or that you could have, or by
yeah, I guess so the best computational ways for, say, counting the number of primes up to x is precisely by essentially doing some counting using the Riemann zeta function. It's a little bit more complicated than just using that formula, but when people compute the number of primes up to some huge number, this is using some sort of numerical verification of the Riemann hypothesis as the most efficient computational way of counting prime numbers. I guess if one way of thinking about the Riemann hypothesis, well, Riemann's explicit formula essentially says if you know everything about all zeros to infinite accuracy, then you know everything about prime numbers to infinite accuracy. The key point of the Riemann hypothesis is maybe that there are some simple properties of zeros which corresponds to important properties of prime numbers. So if you only ask about some weaker property about prime numbers, it might be that can be transported in principle into some question about zeros of the zeta function, and that might be a much easier question to study either computationally or theoretically. So there'll be some questions where if you ask a bizarre question about prime numbers, it's probably not a very efficient thing to translate it into a question about zeros. But there's other questions about prime numbers which only require weak properties about zeros of the Riemann zeta function, and then those are maybe much easier either theoretically or computationally to study on the zero side of things.
All right, thank you very much.
There are also some questions in the chat if you want to answer them.
Okay, hang on. Yeah, let me just. Okay, I can't see the chat whilst I'm sharing my screen, I think.
So the first one is there a formalization of the statement, any pattern of the primes that is impossible occurs infinitely often, except for some finite number of obvious cases?
I don't think that there's any sort of really big catch-all statement. You can, so for the sorts of patterns that I've talked about here, as I mentioned before, these can all be classed as systems of polynomial equations where some of your variables are prime numbers. And so for those things, if you restrict yourself to just asking questions about systems of polynomials where some of your variables are prime, then essentially it is the case that there are fairly explicit conjectures about you should have infinitely many solutions to this system of equations with prime variables or not, depending on a few simple tests that are computationally very easy, say on the system of polynomials. But for more general patterns than that, I don't think there's any catch-all statement, and it can depend a little bit subtly on precisely the question that you're asking. So questions like Mersenne primes or Fermat primes, so primes of the form 2 to the n minus 1 or 2 to the 2 to the n plus 1 are much harder to look at from a sort of computational viewpoint, and also from a statistical viewpoint, the random models are a little bit more dubious for those. And so for things that move outside of polynomial equations, people tend to look at it on a case-by-case basis. Yeah, is it okay if someone reads out whatever other questions there are in the chat? Because I can't see the chat, I think, without stopping my screen share.
Maybe I can ask my own question, which is the next one in the chat, I think. So I was wondering how many of the open problems that were shown at the beginning can be are known to be true, assuming the Riemann hypothesis.
So none of them are known to be true, assuming the Riemann hypothesis. So all of them remain open, even conditionally on the Riemann hypothesis. This is partly because I mentioned that the Riemann hypothesis is really great for large-scale questions, but all four of those questions can somehow be viewed as more small-scale questions, like the gaps between primes, and the Riemann hypothesis doesn't seem to be the perfect way of studying such small-scale questions.
Thanks.
Do we have an upper bound on the density of safe primes among primes?
Yeah, so we can get good upper bounds for this, and we know that the density of safe primes within the primes is 0 as you look at bigger and bigger numbers. So if you pick a big enough number, you're at least 99% certain that your number won't be a safe prime. And yeah, we would expect the density of safe primes to be about around x, to be about 1 over log x within the primes. So the primes are 1 over log x within the integers, and safe primes should be some constant divided by log x within the primes. We get an upper bound, which is a different constant divided by log x, but obviously we don't know a lower bound.
Thank you.
Well, I think that's all for the questions. So thanks again, Professor Maynard, for coming and giving the talk. It was really interesting. So yeah.